Hi everyone, so today we are looking at alkanes and cycloalkanes. Alkanes being the most simplistic and the most fundamental structures in organic chemistry. So we dive right in. So, quick recap. So you should have covered some of this last year, okay? You shouldn't be completely new to alkanes. But just to re-jog your memory, because I know some of you might have forgotten some stuff. Alkanes. So an alkane only contains carbon and hydrogen, and all your carbons within the chain are attached by single bonds. A carbon that has 4 single bonds surrounding it is known as saturated. Okay? So, one thing that I want you to get from the very beginning is carbon should always have 4 bonds. I think it's the most fundamental thing, okay, that you understand. Carbon always has 4 bonds. Hydrogen always has 1 bond. Oxygen always has 2 bonds, and nitrogen always has 3 bonds. This, if you can get into your head now, will make your reactions, okay, your reaction mechanisms, a whole lot easier going forward. So I'm asking you now to take a moment and just remember that part, please. Okay, back to what we're talking about. So, methane. Methane is the most simplistic, okay, the smallest organic molecule. 1 carbon surrounded by 4 hydrogens. We're breaking down our nomenclature here, okay? For an organic molecule that only has 1 carbon in it, the prefix, okay, the first part of the word is always going to be meth. The second part, okay, when we're dealing with an alkane, okay, so known as the suffix, will always be ane or ane. When we pop them together, we get methane. We know we have 1 carbon with obviously no double bonds in between because it's an alkane. So 1 carbon surrounded by 4 hydrogens. 2 carbons, the prefix is eth. Okay, and again an alkane, so the suffix is ane. These 2 carbons, again, because we're dealing with alkane, only have a single bond between each carbon, and each carbon is surrounded by hydrogens. When we have 3 carbons, our prefix is prop. When we have 4, it's but. 5 is pent, and 6 is hex. What about 7, 8, 9, and 10? Well, 7 is hept, H-E-P-T. 8 carbons long is oct, O-C-T. 9 is known, N-O-N. And 10 is dec, D-E-C. Okay? And these are like the alphabet of organic chemistry. We need to know the fundamentals here so we can build on them later on. So if you don't feel confident with them, I'm asking now that you pause this. Okay, and you take a little moment to get used to them again. Okay, reintroduce yourself to these. In organic chemistry, in chemistry in general, there are numerous ways for us to present, okay, our chemicals, our molecules. We can have our chemical formula. So for methane, it's just CH4. For ethane, it's CH3, CH3, okay? And we can also have abbreviated formulas for this. So again, for ethane, if I asked you to write that out in the lab, okay, or maybe label a bit of glassware, you'd probably write it as C2H6 instead, okay? That's our abbreviated formula. Our IUPAC name, okay, so we're going to talk about our nomenclature by our IUPAC system in a moment. For methane, it's methane, we have ethane and propane. When it actually comes to drawing our structures, we typically have a Lewis structure, a skeletal structure. We can also have Fischer structures later on. And it's important that you understand the difference, okay? So our Lewis structure is one that we have absolutely every single thing drawn. Okay, so for methane again, we are drawing our carbon in the center. We are showing that we have 4 single bonds, and at the end of each of those bonds we have a hydrogen. We cannot draw a skeletal structure for methane. Okay, skeletal structures are line structures, and at each end of a line there's a carbon. So if methane only has 1 carbon, we can't draw that. Okay, just be aware of that one. For ethane, again, we have 2 carbons with a single bond in between them. They're saturated carbons, so they have hydrogens all around. Our Lewis structure is giving us all the information we possibly can have about that structure. Propane, a little bit longer, but same gist. In terms of our skeletal structures then, ethane is just a straight line, okay? So again, at the end of each line, we assume there's a carbon. So on our left-hand side of the line here, the left end, that's this carbon here. We don't show the hydrogen surrounding this. For propane, at each end of the line, or each corner of the line, we assume there is a carbon. So 1, 2, 3, and that corresponds, doesn't it, to what we know about propane and the structure here. So, both of these have their benefits. Skeletal structures are great, they're quick and easy to draw when you understand how to do them. As your molecule gets bigger and more complex, it's definitely easier to just draw the line structures. But when we're doing our reaction mechanisms, say we'll start that next week. Although this is good if you have experience with it, I don't think you guys have that experience just yet. Okay, so when you're drawing your reaction mechanisms, I am asking that you always use your Lewis structures, okay? You draw out the full structure. And the reason for this is, as we work through our reaction steps, if we just have our skeletal structure, it's very easy to forget a hydrogen, forget a carbon, label things incorrectly. Whereas we take the time and draw out the full structure, and draw it out each time, we know for certain, okay, or at the very least we can check how many bonds our carbon has, how many bonds our hydrogen has. Have we missed something? Okay? So I'm asking, going forward, when we start the reaction mechanisms, you draw out the full Lewis structure. We're going to look at naming our alkanes. So we have a set of rules really here, okay? So this won't ever really change, and it's a good thing just to have in your back pocket. You will get used to this, okay? This is definitely one of the fundamentals of organic chemistry. So we'll iron it out now. You'll be pros, you'll be flying. So our first rule, we identify the longest chain of carbon atoms. So we're using this guy up here in the corner for an example. So our longest carbon chain is 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5. Why didn't I go this one? 1, 2, 3, 4. We know 4 is less than 5. So 5 carbons is our longest carbon chain. The prefix for a 5 carbon long chain is pent. We're dealing with an alkane, so it's ane for a suffix. So we know that our root name for the molecule is pentane. Next, we identified, do we have substituent first of all? Okay, and a substituent is any additional group here. It could be a methyl group, an ethyl group, a bromo, a fluoro, a chloro, an iodo, etc. And we do have one. And we want to start numbering our carbon atoms so that this will have the lowest possible number. Okay? Now in this molecule, it actually doesn't matter what end we approach from, because if I say 1, 2, 3, this methyl group is on carbon number 3. And the same if I did it this way, 1, 2, 3, this methyl group is still on carbon number 3. So our next step, we named substituent as if it was an independent alkane. So if we looked at this one, it's 1 carbon long, and we know that an alkane with 1 carbon in it is meth. And this time we're not going to say ane, because it's a substituent group, it's going to get the suffix of yl or il, and this becomes known as methyl. And then we combine everything together, we combine all that information. So we know we have a methyl group, we know it's on carbon number 3, and we know our root name is pentane. Putting all that together, we get 3-methyl pentane. What if we have more than one substituent group? Because we know, unfortunately, organic molecules aren't always that simple. They're not always that nice and neat. We can have really, really complex molecules. But if we do have an alkane that has 1 or more substituent groups, we still follow the rules up until that point. Okay? And we still number all the carbons on our longest chain, so that our lowest number possible is dedicated to the first substituent. So, for example, actually we'll do examples in the next slide, we'll walk through it there. So for substituents then, we obviously need to name them. And we name them in alphabetical order, or when we're writing out the full name of our product, we name them in alphabetical order. So ethyl, beginning with E, will always come before methyl, will always be written before that. Even if ethyl is on a later carbon, okay? So in this example, our ethyl is on carbon number 3, but our methyl is on carbon number 2. That doesn't matter, it's still in alphabetical order. So it will be 3 ethyl, 2 methyl, pentane, for example. We can sometimes have the same substituent group appearing several times. We are still going to count what number carbon they appear on. We're going to separate those numbers by commas. And then, if we have, so let's say, for example, we have methyl groups. If we had 2 methyl groups, it would become dimethyl. If we had 3 of them, it would be trimethyl. And if we had 4 of them, it would be tetramethyl. So I'm going to walk through some examples now for the moment, okay? So let's look at this guy. Our longest carbon chain has already been numbered for us, okay? 1 to 6. If we have a carbon chain 6 carbons long, it gets the prefix of hex. Okay, we're dealing with alkanes, so the suffix is ane, A-N-E. So our root molecule is hexane. We then number them in such a way that our first substituent group has the lowest number. And that would mean going from right to left here. So carbon number 1 has nothing on it, but carbon number 2 has a methyl group. Carbon number 3 has 1, 2 carbon groups attached to it, so that becomes an ethyl group. And carbon number 4, we're back to a methyl group. So we have 2 methyl groups. That means we're going to have a dimethyl in there somewhere. They're going to be on positions 2 and 4. And we have an ethyl group. Again, we're going to be working alphabetically. So ethyl, or 3 ethyl, is going to come before 2, 4 dimethyl. When we pop all that together, we get 3 ethyl, 2, 4 dimethyl hexane. We can do another one. Again, we have identified our longest carbon chain, which this time is 7 carbons long. So 7, our prefix is hept, our suffix is ane, because we're still dealing with alkanes. And now we begin to number them, so our first substituent group is on the lowest numbered carbon. And our lowest numbered carbon this time will be carbon number 3, and that has a methyl group on it. Carbon 4 also has a methyl group on it. And that's all our substituent groups today. So we have 3, 4 dimethyl heptane. And one more for good measure. So the longest carbon chain is 6 carbons long. A carbon chain with 6 carbons long as an alkane is going to be hexane. Our chain is numbered in such a way that our first substituent group lands on the lowest numbered carbon. Therefore, we have a methyl group on carbon number 2. We have a methyl group on carbon number 3. And we have an ethyl group on carbon number 4. So it becomes 4 ethyl, 2, 3 dimethyl hexane. So if you need to pause the video at this point and try those yourself, you can. If you need to work them through yourself, you can. You should still have a notebook out beside you, drawing these out, trying it yourself, okay? And again, we can have lots of different substituent groups. We can have a fluorine, a bromine, chlorine, and iodine. We can have methyl, ethyl, butyl, pentyl, etc. We can have loads of different substituent groups. These two guys might look a little bit different here, okay? All that is different is, instead of having our, well, in this case anyway, if we have butane having 4 carbons, this time they're just not in a line. They're in a ring, they're in a circle. In terms of a skeletal structure, the same rule applies. At every corner, there is 1 carbon. So 1 carbon, 2 carbon, 3 carbon, 4. So if I was naming this, I'd count my carbons. 1, 2, 3, 4. so my prefix being but, my suffix being ane because it's still an alkane. I've identified that it's a cyclic or a ring structure, so I'm now putting cyclo before my butane. And I'm still identifying the substituent groups on it, bromine and methyl. We're popping these in alphabetical order. B becomes before M, so bromine's coming first, methyl's coming second. We have numbered them in such a way that our first substituent group is on the lowest numbered carbon. In this case, we can just name this carbon number 1. That's number 1. It's going to be 2 and 3. So we have 1 bromo, 3 methyl cyclobutane. And the same for this guy. So our longest carbon chain is 1, 2, 3, 4, 5. So 5 carbons means pentane. In a ring structure means cyclopentane. We have 1 substituent group here, which is ethyl cyclopentane. We don't need to number this because it's the only one here, okay? But you can call it 1 ethyl cyclopentane too. So, what about the nitty-gritty? Okay, so we're already kind of dealing with structures that we can see using the naked eye. But again, we can go subatomic, okay? We can go down to the bonds in between the carbons and hydrogens, and that's what we have to do. And part of this is referring to the electronic configuration for carbon. This is something, if you did chemistry for Leaving Cert, you've definitely done it. And I'm hoping you did it last year, but I might double check with you guys if you have or haven't. But your electronic configuration, we figure it out anyway using our periodic table. So, for carbon, for example, and carbon is just here on our periodic table, its electronic configuration is 1s2, 2s2, 2p2. So where do these numbers come from? They have to do with orbitals within the molecule, or sorry, within the atom. Okay, so just carbon alone, the carbon atom. So we have 1s2, that comes from our top row. So 1, 2, so 1s2. 2s2 is here. Okay, so 1s2, 2s2, and then 2p2. So p is here, so 1, 2, 2p2. Again, harder to explain online, easier to explain drawing it on a board, but we work with what we got, guys. So 1s2, 2s2, 2p2. If we were to look at the electronic configuration for fluorine, for example, it would be 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 2p5. Okay, for neon it would be 1s2, 2s2, 2p6. Okay, so just working your way through the periodic table. But anyway, we'll go back to carbon. So, we are typically only interested in the outer or the valence shell of any of these atoms because they're the ones that have the electrons available for bonding. For carbon, that would be your 2s2 and your 2p2 orbitals. And if we drew them out, they'd look like this. 2s2 is lower energy than 2p2, so we draw below it. And the 2s2 has 2 electrons occupying that orbital. And they're 2 paired electrons. 2p2, okay, we have our electrons. So remember, one of your rules is that your electrons will always occupy an orbital independently before sharing it. And we'll only ever have a maximum of 2 electrons in each orbital, and they will always have opposite spins. Now, it's only these lone electrons here that are available for bonding. And that would, if we just took this graph as is, that would lead us to believe that carbon can only have 2 bonds. And we know that's not the case. We know carbon has 4 bonds. So, what's going on here? This doesn't make sense. So, something has to happen. Something has to change here to allow us to go from this, that we only have 2 bonds in carbon, when we know that carbon really has 4 bonds and always has 4 bonds. So, let's just try and figure something out. What we need to do is hybridize our orbitals. So I'm hoping you may have heard of sp3 hybridization. And by hybridizing them, so combining your sp or your s orbitals and your p orbitals, we will generate 4 equivalent orbitals that are all of equal energy and all available for bonding. They look like this. Okay, so they're 1 part S and 3 parts P. Okay, adding up to 4 total. This is something that can confuse students a little bit, so what I might do is I'm going to let you just be introduced with this week, and I might just put up a short video in addition to your lecture next week to work through this, okay? But the main takeaway point for you at the moment is our alkanes, all alkanes and all carbons within our alkanes are sp3 hybridized. When we look at alkenes, they'll be sp2 hybridized, and our alkynes will be sp1 hybridized. That's the main takeaway I need from you guys this week. Okay, so now, and this makes sense now, doesn't it? So this hybridization allows carbon to have 4 equivalent bonds. And we know that's how carbon works practically. We know carbon will always have 4 bonds. And that is down to our sp3 hybridization. So, within each orbital you have electrons. And again, electrons are negatively charged. And they're going to position themselves in such a way that they are as far away from each other as possible because they repulse each other, okay? They push each other away. And this shape is known as a tetrahedron. And the angles in between each orbital is 109.5 degrees. And just a little heads up, again, this can be a common question. If you write, or if I ask, okay, what is the bond angle for sp3 hybridization, and you say 109, you will not be right. I will not give you the marks. It will be 109.5 that gets the full marks. Make a mental note, please. When we draw it out, it looks something like this. So each of these red balloons represents 1 bond for carbon, okay, an sp3 hybridized bond. And we have 4 of them because carbon has 4 bonds. Let's look at actually a molecule with that, okay? So our simplest one is methane. So we have our carbon with our 4 sp3 hybrid orbitals, all of equal energy. We have 4 hydrogens. In each of these little balloons are electrons, okay? Same in our hydrogen little balloons here. And again, it's the interaction between those electrons, okay? The sharing of those electrons in this case, that form bonds. So a bond is formed between the electrons of carbon and the electrons of hydrogen. And remember, this is a covalent bond, okay? These electrons are being shared between the two. And we get our methane molecule. Again, we can draw methane out in a number of ways. We can have our Lewis structure. Okay, flat on a piece of paper, but it shows us every single thing that we really need to know. Okay, we know the carbons and we know the hydrogens are in there. We can also have a 3D ball and stick model. And this again, so when we're thinking of organic chemistry, try not to think of it as flat on a piece of paper because it's not. These are atoms and molecules that are existing in a 3D space, and therefore they have angles. They have a back and a front and a side and a side. So we can draw them as such. Okay, here we're actually drawing the tetrahedron geometry. You can clearly see the bond angles, okay? We can't see that in the Lewis structure. We still have the information we need as in going forward for our reactions, but we don't see the geometry, and we don't see the bond angles. We can also have 3D ball models, and these are important. So again, if we could shrink ourselves down to the size of, an atomic size, we would see that a carbon atom is far bigger than a hydrogen atom. Okay? You could have something like, if we go back to our periodic table actually quickly. If we go back to our periodic table, we know as we go down our periodic table, the number of orbitals in our atom gets bigger. So if we looked at bromine, okay, and we were able to look at that in real life, we would see that the size of bromine is far bigger than carbon, and it's definitely far bigger than hydrogen, okay? So they're bigger and bulkier, and that isn't always represented on paper. So again, it's important for us to note that not only do they exist in a 3D space, they're not all the same size. Okay, so in this, you can see that our carbon is far bigger than any of our hydrogens, and it's a far bulkier molecule than we might initially think. We also have a Fischer projection, and a Fischer projection is a good way for us to represent a 3D molecule on a 2D surface such as paper. When we see a dashed line like this, it means that this hydrogen here is moving away from us, okay? So it's going behind the molecule. When we have a solid wedge like this, it means it's going towards us, okay? It's coming off the page. This is something that we do encounter later on, particularly in stereochemistry and even beyond that. So it's nice to familiarise yourself with the dashed line and the wedge. So let's look at some conformations. We've already said that our molecules are 3D. They exist in 3D space. We know from last week in our IOR that they're constantly moving, aren't they? So they vibrate, the bonds within them vibrate. And now we're telling you that they rotate as well. So going from something that was very rigid and stagnant and nothing really happening to really mobile and interesting, I suppose, molecules. Okay, something is always going on. So anywhere around a carbon-carbon single bond, rotations can occur. And these obviously result in different shapes of our alkanes. And the different arrangements are called conformations, okay? And these, again, are constantly moving back and forth, so they're interconvertible. So just because you might see one structure in one conformation, it doesn't mean it stays in a conformation. Again, it will rotate back and forth into its alternate conformations. And we're going to look at ethane as our example first. So, ethane can exist in an eclipsed or a staggered conformation. And usually, we can look at it in a 3D space again. We can look at them in our models. And again, this will be better in a face-to-face class. These images don't do it justice in my opinion. So we're going to look at it. We're going to take our 3D images and flatten them out and draw them in such a way that we can actually see the clear difference between an eclipsed conformation and a staggered conformation. So, our eclipsed. We can represent our eclipsed and our staggered as dash wedge conformations, as sawhorse, or as Newman projections. Your dash wedge gives a good indication. Sawhorse, a slight angle, a little bit better. The one that we are always interested in is our Newman projection. Okay, and when we start to work through it, it will become a little bit clearer, I hope. But this shows us clearly what is actually going on in each conformation. So let's look at our eclipsed Newman projection here for ethane. First of all, you need to think that you are looking at this molecule face on. So you are directly staring at the first carbon of ethane right here. And that would mean the second carbon is directly behind that. Okay, so this large circle here is a carbon. Now, in an eclipsed conformation, your hydrogens are eclipsing one another, okay? So they're directly behind and in front of each other. And you can see that here. This, and again, if we think of these as 3D shapes, as 3D objects, these two might be bumping into each other, just as these two might, and these two. And this is only going to get worse the larger the substituent group becomes. And again, they're not just balloons, okay? In this hydrogen atom here, it has electrons, as does this one. Electrons are negatively charged. They do not want to be beside something else that's negatively charged. They're going to try and repulse each other, okay? Repel each other. So, this becomes known as our least stable conformer. So, what would be more stable? How could we remedy this? Well, we can stagger them, can't we? So again, if we're looking here, we are pretending that we are facing our ethane molecule head on. So smack bang in the middle here is our first carbon of ethane, and directly behind it is the second carbon. The difference this time is that we have our hydrogens of our first. They are staggered against the hydrogens on our second carbon. And that looks way better. Okay? This is far more stable. This hydrogen is not competing for space with this hydrogen, or this one, or this one. They are spread out as far as they can. There is no repulsion there. So therefore it is most stable. And again, this is a common question. You could be asked to draw ethane or a more complex, a more substituted molecule. Draw it out in both forms of Newman projection, so eclipsed and staggered, and identify which one is most stable. And it's always going to be staggered. What about when we start adding substituent groups? Well, the body of our Newman projection is always based on ethane. Okay, so it's always one carbon here and a second carbon behind it. That's it. Anything additional add on to it, particularly any carbon chains, they become substituent groups. So in this case, in propane, we take the body of ethane, we make that the body of our Newman projection, and this final methyl group becomes a substituent group. And we pop it up here. Again, same rules apply. We draw them as an eclipsed, and we can draw it as staggered. And again, if we think of our carbon molecule as a 3 molecule, carbon atom, we've already said carbon's bulky. Carbon with 3 hydrogens with their own orbitals surrounding them, bumping into a hydrogen here with its own orbitals around it, is going to be pretty tight with space. And again, it's going to be less stable. Again, if we draw it as a staggered conformation, we can see carbon and its 3 hydrogens surrounding have far more space. It's not competing here, and it's not bumping into anything else that has its own electron orbitals. Again, we can get more complex structures. This time we have butane. So same rule applies. You are taking the two middle carbons here, so drawing those out as ethane essentially. One carbon here, one carbon behind it. The first group here, okay, is added as a substituent group, as is the last methyl group on the back carbon. So it still is butane. 1 carbon, 2 carbon, there's one behind it, 3 carbon, and 4 carbon. Still butane. This time, we now have 2 substituent groups. And things are a little bit bulkier again, aren't they? So again, we have carbon, which is a larger atom, with 3 hydrogens around it, bumping into another carbon with 3 hydrogens around it, bumping into each other. If they're side by side like this, it's known as staggered gauche, and the angle between the two is only 60 degrees. The likelihood of those bumping into each other and repelling each other is high, and it's going to be less stable. What are we comparing it to? We're comparing it to a staggered anti. So again, common sense really. If you say these two are bumping into each other, they're repelling each other, it's unstable. What's the easiest thing we can do? Well, we can move them further away from each other. So we can move one all the way down here, increasing the dihedral angle to 180 degrees, and that is far more stable. Far less repulsion between electrons here and electrons here. They're happy out. So, staggered is more stable than eclipsed, and staggered anti is more stable than staggered gauche. We're going to look at cycloalkanes. So we've already briefly met them. Okay. Here, same rules apply. Every corner has a carbon. 1 carbon, 2 carbon, 3 carbon. If we had 3 carbons in a line, we would say it's propane. If it's in a ring, we say it's cyclopropane. If we have 4 carbons, each corner has a carbon. 1, 2, 3, 4. If it was just a linear molecule, we would say it's butane. If it's in a ring structure, we say it's cyclobutane. Same as for pentane, this becomes cyclopentane, and the same for hexane, becomes cyclohexane. Okay, not too difficult so far. We can, okay, we're introducing something new here, we can have cis or trans isomers. Okay, cis means being on the same side. Trans means being on the opposite sides. So your ring has a top and a bottom. Again, you're trying to use your own spatial awareness here, okay? Your 3D space, not just thinking of them as a flat square on a page. Okay, you have to think of this in a real 3D space. So, if we have two substituents on the same side, they become known as cis. And if they're on the opposite side, they're known as trans. And what we're talking about are sides here. Okay? This is where I recommend you draw your Lewis structures. Right now, it's very easy to forget that you have two hydrants sticking out of each corner here. It's a little bit harder to forget with our or a little bit harder to remember with our skeletal structures. So this is where I recommend you draw the structure out for yourself and draw it as a Lewis structure. So draw everything that's part of that molecule, count all the bonds for all your carbons, and make sure they have 4 bonds for each carbon, 1 bond for each hydrogen. So if we do that, we can see in this case we have cyclopentane is our root structure essentially here. And again, if we think of this as a 3D, okay, or existing in a 3D space, on the bottom of the ring we have 2 hydrogens, and on the top of the ring we have 2 methyl groups. The methyl groups here are on the same side, aren't they? They're on top of the cyclopentane ring. And if they're on the same side, they become known as cis. Okay, so this is cis and this is trans. Okay, so they are facing, this is the same. Okay, so these are both cis. So our dark dashed or dark wedged lines here, still facing on the same way. This is still cis. And this is cis. And again, a rule still applies here for numbering, okay? Numbering so that our first substituent group is on the lowest number carbon. So this is 1, okay? Doesn't matter which one you choose to be 1. 1, 2, 3, 4, 5. So 1, 2, dimethyl cyclopentane. And because they're on the same side of the ring, they are cis. So cis 1, 2, dimethyl cyclopentane. What about trans? Trans look like this. They are opposite each other. Okay, one methyl group is on top of the ring, the other methyl is on the bottom of the ring. We can also show it with our dash and our wedge lines. One of our methyl groups, again, we said our dark wedge line says it's coming towards us, okay, it's coming forward in the page. Our dashed line means it's going away from us, it's going into the page. So that's representing here. This one is going up and this one is going down. Still the same structure, okay, so as in it's still 1,2-dimethyl cyclopentane, except this time it's trans 1,2-dimethyl cyclopentane. And again, cycloalkanes can have different conformations. And again, we're trying to think, so something like this, right? It's a pretty busy molecule, isn't it? So we have 1, 2, 3. So we have propane. It's in a ring structure, so it's cyclopropane. It's unstable. We're going to ask why. Okay, have a little think there. Why is it unstable? Its carbon-carbon bonds are 60 degrees and all the hydrogens are eclipsed. Okay, they're all overlapping each other. They're all on top of each other. And that's the reason it's unstable, isn't it? They're all bumping into each other. All their electrons within their orbitals are side by side, they're repulsing, repelling each other. Makes it massively unstable. Okay, cyclobutane has a bond angle of 90 degrees. The ring is puckered. Okay, so it's puckered as in it's not a flat structure. Okay, there's a slight bend here in the structure. And this slight bend reduces the eclipsing of our hydrogens. There's a bit more space for them to just be by themselves. So it's less unstable or more stable than our cyclopropane. We have cyclopentane. So again, a far cry from the pentagon that we usually draw, okay, that flat shape that we usually draw. This time we have puckering again, okay, so slight bending in that structure. We have an increased bond angle, And again, we have less eclipsing of our hydrogens. So this puckering, this increase in bond angle is increasing the stability and reducing the eclipsing of our hydrogens. And the main one we usually look at is cyclohexane. And again, it's not flat. It's not a flat molecule and it's not planar, okay? So again, it exists in a 3D space. And the ring itself is really flexible because we have loads of single bonds in between those carbons. The most favoured conformation is known as the chair conformation, but there is also one called boat. In the chair conformation, and that's the one we're going to focus on, the bond angles are all 109.5 degrees, and all the hydrogens on adjacent carbons are staggered. And we've already said this, the staggered is always far more stable than the eclipse. And when we draw our chair, it looks like this. Okay, so a lot of puckering. And here, we haven't drawn in all our hydrogens yet. Again, it's a 3D, it's a flexible molecule. So it can look like this, or the bonds may change and it will look like this. When we fill in our hydrogens, we can do it, or when we just fill in the substituents and our hydrogens, it can look a few different ways. So there's two sets of hydrogens in our chair conformations, and these are axial and equatorial. This is axial, okay? So if you want to think along the y-axis here, okay? So they're all going up and down. So your hydrogens are lying alternately above and below the plane of the ring. So the plane of the ring is here, okay? Just the ring itself. So you have hydrogens up here and hydrogens down here. We also have equatorial, and they are lying along the equator, okay? They're lying along the side and they're pointing away from the ring. Again, I want you to think for a moment, which one of these is most stable? Which one of these allows our hydrogens or any other substituent group to be as far away from each other as possible? Which one would allow them to not be eclipsed by each other? Okay, when we draw them out, they can look like this. So, our cyclohexane, we have 12 hydrogens here, which is quite a lot. So we can see when we add in our hydrogens, it becomes a very, very busy molecule, doesn't it? We have 6 axial, we have 6 equatorial. So 6 axial are facing up and down. So here's 1, 2, 3, 4, 5, 6. And everything facing outward and away from the molecule is equatorial. So 1, 2, 3, 4, 5, and 6. So it's already busy enough, but this is relatively stable by itself. It's happy enough here, okay? But what happens, we'll talk about this first. So our ring flipping. So again, the conformation can change, okay? It flips quite readily because it is a flexible molecule. So when your ring flips, your axial hydrogens become equatorial and your equatorial become axial. And it's just a note that this can occur, okay? So your axial, what once was axial, becomes equatorial. What once was equatorial becomes axial. That's all you need to know here. Now, this is where we need to start thinking about our 3D space again. What happens if we have a mono-substituted cyclohexane? So, when we're talking about cyclohexane there, in our chair conformation, we had nothing but hydrogens there. If we add a substituent group, so something like a methyl, an ethyl, a propyl, a butyl, a fluoro, a chloro, etc., it can go into 2 possible different spaces. So one where your substituent is axial and the other where the substituent is equatorial. So your most stable conformation is where the substituent is placed in the equatorial position. Okay, so we're going to look at something like methyl cyclohexane. When we draw it, here, okay, when we draw it on the equator, this bulky methyl group is facing away from the structure, okay? So that means this bulky carbon with 3 hydrogens is away from all of those hydrogens there. Has a lot more space and it's not going to be repelled. And this is more stable than if we had our methyl group in the axial position, because again, if you think, and you draw it out yourself now, if you draw out your hydrogens all around here, remember we said how busy this molecule is? This is right in the thick of that mess. Whereas here, at least, it's out facing away from the rest of the molecule. Now, so the preference of our alkyl groups for equatorial and axial. This depends on the size of your alkyl group. So for methyl cyclohexane and ethyl cyclohexane, most of your molecules have an alkyl group in the equatorial position. For branched alkyl groups, so getting bigger, okay, equatorial is even more marked, 97%. And if we have even longer chains here, bulkier, more branched, nearly all of it is going to be equatorial. So we can see that space, okay, so not only the space taken up by the substituent group, but also the space that the equatorial position allows is really, really important there. So again, try to keep in mind that these CH3 groups are not flat and compact like this. If you draw out 3 CH3 groups bound together, that's a big, bulky substituent group. Okay, it's not neat and compact like this. So equatorial is the most stable conformation here in our chair conformation. Guys, we're going to leave it there for this week. Okay, next week we are going to be looking at the reactions of alkanes. Will become, a little bit more challenging. We'll need to have a think about that there, okay? So what I'm going to ask you to do this week is you are going to do the nomenclature quiz that I set up on Moodle to practice your naming of your molecules, and you're also going to complete the exercise sheet in which you're going to draw some of your alkanes and your cycloalkanes. Again, these are ungraded. These are practice. These are sheets that we'd be doing if we were in the lecture hall. So do attempt them. Do upload your drawings. So you're going to be using the Microsoft Lens app. You can download that on your phone or on your tablet, scan in the image and upload that directly to Moodle. So give that a go and let me know how you get on, and we will chat then next week.